Now let's discuss about the periodic trend of ionization energy. So this is a upright property. So I call it upright property. I will explain why it is called upright property. Just let me take the pen. Yeah, so first thing we have to understand that what is the concept of ionization energy. Now let's try to see this thing. You see, this is a kid who is holding a lot of balloons. Now what you can do, you can cut a wire, a rope, right? If you cut a rope, what will happen? One of the balloon will fly, right? Similarly, you can cut another rope, and similarly another balloon will fly, and those balloons will go out of his hand, out of his control. Okay, so what kind of energy you are providing? You are cutting the rope, and that's why these balloons can get free. Those are getting free and out of this boy's control. So similar concept you have to visualize in case of atom. In case of atom, you see they have electrons in the shells. What you can do, you can knock out this electron. You can provide some energy so that this electron will go away, and that will go out of control of this atom. So as this electron is going away, so this electron is minus charge, negatively charged, so this atom will become positively charged. So let's see the definition now. So the amount of energy required to knock out the loosely bound electron in the outermost shell in an isolated atom in the gaseous phase to generate a charged cation is referred as the ionization energy of the element. I know this looks a big definition, but let's try to understand it by small portions. So the amount of energy required, so the amount of energy that we are supplying to cut these balloons, okay? That's what, that amount of energy, that is referring to the ionization energy. To knock out the loosely bound electron. So we can knock out the outermost electrons, or the electrons which are not tightly bound, which are loosely bound, so that we can easily knock them out, right? We can provide some energy and it will go out. In the outermost shell, as I already mentioned, that we will knock out the electrons from the outermost shell in an isolated atom. So this one is very important. In case of the definition of ionization energy, it has to consider the isolated atom. So this atom cannot be with the other atoms, or it cannot be bonded with another atom. It cannot be bonded with B, or it cannot stay with the other A type of atoms. If it stays with other atoms, no, so there will be some interaction. So that interaction energy also you have to keep it in mind. You have to calculate. So you have to calculate more things if it is in surroundings of other atoms. So what you have to do, first you have to provide some energy, and you have to take out this atom in seclusion. This has to be an isolated atom. No one should be in its surroundings. Only then this ionization energy definition you can apply. And in the gaseous phase, so you have to take it, this ion or atom, to the gaseous phase to generate a charged cation. So as you are taking electrons from here, you can see if you are taking electron from here, so you will generate a cation, and that is referred as the ionization energy of element. So the energy you are providing, to take electrons from the outermost shell of an isolated atom, that much energy is called ionization energy. Now we will see these definitions or some examples. In case of this, see aluminium. So aluminium has 13 electrons. Now what will be the arrangement? I'll do it here. Just assume this one is the nucleus of aluminium. Then we have 2 electrons in the first shell, 8 electrons in the second shell, and 3 electrons in the third shell. So 2, 8, and 3. So in our outermost shell, we have 3 electrons, and all these 3 electrons we can take one by one. So what are we doing? First, we are taking 1 electron, and the ionization energy is this 578 kilojoule per mole. Now, when we are taking 1 electron, so we are doing 3 minus 1. So in the last shell, now we have 2 electrons. So if there are less number of electrons and more number of protons, we know in case of cations, the electrostatic interaction will be more, and those outermost electrons will be now tightly bound. They will feel more attraction towards the attractive girl or the nucleus, right? So now when we are trying to take out another electron from this aluminum plus, from this, if we want to take out another electron, so we have to supply more energy. That's why this IE2 is actually greater than this IE1, ionization energy 1. Now we have taken out another electron, supplying more energy. So now we have, now we have only 1 electrons in the third shell or outermost shell. So in total now we have 13 protons and only 11 electrons. So now we have lesser number of electrons and much more lesser. So the attraction energy of the nucleus will be more and more. So when we try to take out another electron from aluminum 2 plus to generate aluminum 3 plus, we actually have to provide much more energy. And you can see this much energy we have to provide. 2744.8 kilojoule per mole, which is actually more than the summation of its IE1 and IE2. Even if you sum these two, this number is much greater. So you can take out electrons from an atom one by one, but as the number of electrons are decreasing and the number of protons are increasing in the ion, so they will experience more and more attraction. So you have to provide more and more energy to take out the outermost electrons. Okay, clear? Now let's see the periodic trend. So you can see I have already mentioned it. This is a upright property. So if you see the periodic table, the ionization energy increases from left to right in a period, and uh, if you go from top to bottom, the ionization energy actually decreases. So we can say that ionization energy increases from bottom to top. So if you go from bottom to top, the ionization energy increases. So actually we can say that this is increasing in this upright corner of this periodic table, right? So that's why I tell it as UR property or upright property. Now let's see this 3D periodic table of ionization energy for your easier visualization. Now you can see from left to right, the ionization energy is increasing. Even if you consider this part only p block element, just see from left to right, the ionization energy is increasing. And from top to bottom, the ionization energy is decreasing. So actually from bottom to top, the ionization energy is increasing. So this corner is having the most ionization energy. So this graph is based on the first ionization energy. Okay. Now let's see the detail of the periodic trend. First, we will see along period. What are the factors that are working along period? So along period, principal quantum number is fixed. So the number of shell is fixed. So if you go from boron to carbon to nitrogen, oxygen, the principal quantum number or the number of shell is fixed, or the number of orbit is fixed. Effective nuclear charge increases. We have already seen as we go from left to right, we are putting more and more protons in the nucleus. So the girl is more and more attractive. So that's why that girl attracts the lovers or the electrons more, right? So the effective nuclear charge increases from left to right along period. The size gradually decreases. The atomic size also is decreasing from left to right because of the increase in the effective nuclear charge, right? So all these factors actually increase the ionization energy from left to right. Now another factor, this electron-electron repulsion, that also increases from the left to right, but actually this is negligible factor in case of ionization energy. So that's why I'm writing it in red. Okay, so this factor is very minor, and you have to neglect this factor. So thus, the electrostatic attraction towards the nucleus increases along the period, and ionization energy goes up. Just simply try to understand, if we have a smaller atom where the electrostatic interaction is more, and if we have a bigger atom, in case of bigger atoms, the shells, just consider that we have a bigger atom and these valence electrons are also far apart. So if these valence electrons are far apart, it will not have much control. The nucleus will not have much control on the electron, right? So you can easily take out this outermost electron. But as the size is small and effective nuclear charge is more in this atom, so if you try to take out this electron, you have to put more and more energy, right? That's why as you go from left to right along a period, the effective nuclear charge increases, size decreases. So all these factors make this electron tightly bound or tightly attracted towards nucleus. So that's why it takes higher energy to take it out in the gaseous phase. Okay, so it takes higher energy. So that's why the ionization energy is more. Yeah, so there are some exceptional cases. For example, I can show you here. So you see, just see this: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So if you see this one, so we are expecting the ionization energy will increase along the period, right? That is happening from lithium to beryllium. But for some reason, from beryllium to boron, it is actually decreasing. And again, boron, carbon, nitrogen, these are increasing. So the trend is fine here. But again, here from nitrogen to oxygen, the ionization energy is decreasing. So there are some exceptions, and we are going to talk about that. So according to general periodic trend, oxygen should have higher ionization energy compared to nitrogen. Yeah, because nitrogen is having atomic number 7, oxygen is having atomic number 8, right? So oxygen comes right to the nitrogen. So according to the periodic trend, oxygen should have higher ionization energy. But it is having lower. Why? Due to the half-filled electronic configuration, nitrogen has higher ionization energy. So I will explain it later in detail, but just in a brief, I will say this electronic configuration. See this electronic configuration. This electronic configuration I have already taught in the previous lecture. If you have not seen, you can go and check the lecture 5. You can see it is 2p3 and this one is 2p4. Now if I draw this 2p, for nitrogen we have 2p3, so one electron here, one electron here, and one electron here. Now same thing for oxygen. So one electron here, second electron here, third electron here, and fourth electron. Note down, I have drawn 3 electrons, all 3 are in up spin. Now when I put the fourth electron, that will share with this electron, and now this cannot be the up spin, so this electron will be down spin. Due to Pauli's rule, the electrons in the same shell cannot be of the same spin. Okay, so as I am putting the fourth electron, I will put it as a down spin. Now in this case, in case of nitrogen, we have 2p3 configuration. So this is half filled. This is called half filled because we can at max put 2 electrons, 2 electrons, and 2 electrons. We can put maximum 6 electrons in this 2p orbital, but we have put only 3 electrons. So this is half filled. Whereas in case of oxygen, it is 2p4. So here 2 electrons, here 1, and here 1. So total 4 electrons. So this half fill and full fill shells, they have surprisingly high stability because they are having higher exchange energy. I will explain this exchange energy in after some slides in this lecture. So because of this half fill configuration, it is having more exchange energy. So the exchange energy means this electron can go here, this electron can come here, or this electron can go here, this electron can come here. So all this kind of possible exchange can happen. So that's why this nitrogen is having higher exchange energy, and it is more stable. Because of that fact, if we try to remove one electron from this nitrogen, so this ionization energy will be much high compared to the oxygen's ionization energy. So from oxygen, if you want to simply remove one electron, we can simply remove this electron. But from nitrogen, if you want to remove electron, so that time the ionization energy will, the exchange energy will decrease. So these electrons can exchange their positions, and that's why they have better stability. But if you remove one electron, so that time their exchange energy will decrease. So that's why this nitrogen will not let it go. It will not let the electron go. Okay, because of that reason, the ionization energy of nitrogen, first ionization energy of nitrogen is more compared to the first ionization energy of the oxygen. Okay, but now consider the second ionization energy. So we have already removed one electron. So I'll just erase this. Wait. So we have removed one electron. Just assume we have removed this electron from the nitrogen, and we have removed this downspin electron from the oxygen. So in this case, now we see there are only 2 electrons, and the exchange energy is also very less for nitrogen because it is not half filled. But now this O positive, that is actually half filled. There are only 3 electrons, and in this half filled configuration, they have higher exchange energy. So if we consider the second ionization energy, if you want to try to if you try to remove one more electron, so that time we have to spend lesser energy in case of N plus, but we have to spend much more energy in case of O plus, because O plus got stable state, this stable half filled state. Now you are trying to disturb it. You are trying to take one electron again. So that time this O plus will not let it go. It will not let the electron go. So that's why you have to put more and more energy. Okay, got it? Let's see some more cases. For example, if you see phosphorus and sulfur, so similar to the nitrogen and oxygen case, phosphorus is having 3p3 and sulfur is having 3p4. So that's why if you consider the first ionization energy, the phosphorus will have higher first ionization energy compared to the sulfur, right? But now it is becoming phosphorus positive and sulfur positive. Now it has 3p2, only 2p electrons, and sulfur positive is having 3p electrons. So now this S plus sulfur positive is now half filled. So it is much stable. So now if we try to remove one more electron from phosphorus positive and the sulfur positive, so that time we are removing electrons from this 3p2 and 3p3. So this time this second ionization energy will be lesser in case of P plus, whereas it will be higher in case of sulfur positive. But this is not universal, okay? So this works in this concept of exchange energy and gaining stability through this exchange energy, that works well in case of lighter elements. So this exchange energy concept does not have effect in the heavier elements, and they follow normal periodic trend. So if you go along the period from left to right, it will increase. The ionization energy will increase. That thing happens in case of this antimony, tellurium, bismuth, and polonium. If you see, this is having 5p3, 5p4, and bismuth and polonium, they are having 6p3, and 6p4. So from the half-filled nature, we expect this antimony will have higher ionization energy, first ionization energy, but that is not true. You can see antimony is having lower first ionization energy. Sorry for that. So antimony will have a lower first ionization energy compared to the tellurium. You see it is having higher first ionization energy. Similarly, from the exchange rule or from the half-filled concept, we might expect that bismuth will having higher ionization energy compared to this polonium, but that is not true. So if we see, this will be actually first ionization energy, sorry. If we see the first ionization energy of this bismuth and polonium, we can see bismuth is having lower ionization energy, whereas polonium is having higher ionization energy. Now let's try to remember this trend. How we can remember this ionization energy trend. So if you take these three periods, period 2, 3 and 4, and you will see, so these are the lighter elements or the lighter atoms. So they actually, in these lighter atoms, the concept of half field and exchange energy, that actually works well. That already we have seen in case of nitrogen and oxygen, right? For that, the ionization energy trend is like this, So it first increase, then it will decrease, then again it will increase, then again it will decrease, and again it will increase. So this is how I remember it based on 2-3-3 formula. So first I will increase till 2 elements, means lithium and beryllium. Then I will decrease 1, I'll come to boron, and then I will take 3 more elements, means boron, carbon and nitrogen, that will increase. And again I will come down in case of oxygen, I will come down, and then again I will increase 3, oxygen, fluorine and neon. Similarly, in case of period 3, I'm sorry, I'm using a very primitive setup. Yeah, so again in case of sodium and magnesium, so these two will increase. Then again in case of aluminum, it will decrease. And then again aluminum, silicon, phosphorus, it will increase. Again from phosphorus to sulfur, it will decrease. And again sulfur, chlorine and argon, it will increase. So I remember this trend of these three periods as a 2-3-3 formula. And these ones, these elements, for example, beryllium and nitrogen, or magnesium and phosphorus, these peak elements, they are actually full filled and half filled. So that's why they are having higher stability, higher exchange energy. If you see the electronic configuration of beryllium, it is 2:2, that is full filled. In case of nitrogen, it is 2p3, that is half filled. So these full filled and half filled configuration, they have higher exchange energy, and that's why they are having higher ionization energy compared to their nearby atom, right-sided atom. But as I said, that this concept of exchange energy and half filled concept, that works well in the lower atomic number elements, but in case of these higher atomic number elements, that do not work. And for the next period, this will be period 5. For the period 5, you can see it will just monotonously increase. The ionization energy will increase. Similarly, in case of period 6, it will increase, and then it will decrease for 1, and then again it will increase. And this element is actually lead. So cesium, barium, thorium and lead, that will increase, and then in bismuth it will decrease, and then again it will increase. So when I used to prepare for competitive exams, I used to remember these trends. First 3 periods will be 2-3-3 formula, next period will be monotonously increase, and the last next period will increase till lead, then decrease, and then again increase. So as I have already mentioned, this half filled and full filled concept, you can see in case of boron it is 2p1, and p electrons can p orbital can take at most 6 electrons. Now we have only 1. In case of carbon we have 2 electrons, and in case of nitrogen we have 3 electrons. So 3 is actually half filled. At most we can have 6 electrons, we have 3 electrons, so that is a half filled configuration that is having higher exchange energy, so that's why it is more stable. So this half filled and full filled concept we will learn in the later slides. Yeah, so this is the filling of electrons that I have already discussed in the previous lecture. So you can see you have to learn this electronic configuration. So first electron goes in 1s, and that is 1s1 in case of hydrogen. Then the next electron, that also goes in 1s, and in case of helium we have 2 electrons, and those spins are opposite in nature. One is up spin, another one is down spin. Now the next electron goes in 2s, and we get lithium. The next electron goes in again 2s, and we get 1s2, 2s2, that gives beryllium. So here 1s2, 2 electrons are oppositely spinned. Here also both the electrons have opposite spin. Now the next electron goes in 2p, and if we put one more electron, that will go here, another 2p, And if you put one more electron, that will also go in another 2p. And after that, if you put one more electron, that means 2p4 in case of oxygen, that electron will go here and that will have downspin. In case of fluorine, we will have one more electron, and in case of neon, we will have full filled configuration. So this is the electronic configuration you can see. And if you put one more electrons after this 2p, that will go in 3s. The next electron will also go in 3s. It will paired up. And if we put one more electron, that will go in 3p in case of aluminum. And then we put one more electron in silicon, phosphorus. So this 3p3, this will be again half filled configuration. Now we put more and more electrons, and in case of argon, we get again full filled configuration. So this is how you can put electrons and you can determine the electronic configurations. So now we are going to understand the concept of exchange energy. So in case of lithium, we have 1s2 and 2s1, only one electron. In case of beryllium, we have 1s2, 2s2. Now this beryllium in 2s, now it has 2 electrons. So this is actually full filled. Now these electrons, or these full filled electrons, are actually called, they are having higher stability. Now I will explain it in case of nitrogen and oxygen. Let's see again. In case of boron, we have 1s2, 2s2 and 2p1. In case of carbon, we have 1s2, 2s2 and 2p2. So the next electron will go here. Now we will do the nitrogen. We have 1s2, 2s2 and 2p3. In case of nitrogen, we have 1s2, 2s2, 2p3. Now this 2p3, so all the px, py and pz orbitals, they are having 1 electrons. This is actually half filled configuration. So these electrons, which are half filled, can now actually change their position. What I will do, I'll just draw it like this. So this is the crude idea which I'm telling you to understand this exchange energy. Now in the 2p we have 3 electrons, right? So let's write it as 1, 2 and 3. Let's consider it as 1. This one is as 2, electron 2 and electron 3. So this can be in this order, or this can be like this: 2, 3, 1, or this 2 and 3 can exchange their positions, right? So it can be 3, 2, 1. So all these possibilities can happen. So these electrons can change their place. The thing is, these electrons are occupying the shells. That's why they can change their place. If it is a vacant shell, you should not calculate it. I mean, you should not consider it that this electron will go here in this position. Okay. So if in this case, in case of carbon, these 2 electrons can change their positions. Similarly, in case of nitrogen, all the 3 electrons can change their position. Now this gives higher exchange energy. That is called exchange energy. That electron can go from here to here, and this electron can go from here to here. So this is more in case of half filled configuration. But when we have 2p4, p1, p2, p3 and p4. Now you might say that still these 3 electrons can change their position, but actually not, because these are paired electrons. These electrons have their interactions, and though these 2 electrons can change their position, but the exchange energy actually decreases from the compared to the nitrogen. Now that exchange energy will increase again in case of neon. If you see the electronic configuration of neon, so that will be actually 2p1, 2p2, 2p3, then 2p4, 2p5 and 2p6. Now these 3 electrons which are having half spin, they can change their position, they can have exchange energy, and these 3 electrons which have down spin, they can change their position and they can have exchange energy. So this configuration, full filled configuration, is actually having 2 times of exchange energy compared to this nitrogen, right? So this is having 2 times of exchange energy. But there is another thing that we have to consider, is the pairing energy. So as the electrons are paired here, So we have to subtract some term which is called pairing energy. For example, if we write exchange energy like E, so for 3 electrons we have E3 exchange energy. Okay, now here it will be E3. This 3 electrons generates E3, the upspin 3 electrons, and another E3 for the downspin 3 electrons. So let's try to understand again. Here we have 3 upspin electrons that can change their position, and that will gain this E3 term, E3 energy, stability. And these 3 electrons which are having lower spin, they can also exchange their positions, and that will have another E3 exchange energy. Apart from this, we have some pairing energy also. That actually we have to subtract, because there are 3 pairs. When we are trying to exchange these electrons, we are breaking that pair. So if we take out these electrons, I will take the laser pointer for this. Yeah, see. So this is a pair, right? And this is another pair. This one is another pair. So these electrons are close to each other. They have some kind of interaction. They have some kind of energy going on, energy exchange going on in between them. So when I'm trying to do exchange of this downspin electron with this downspin electron, so I'm trying to change the position of these two. So that time first I'm breaking this pair, then I'm breaking this pair, and then I'm changing the position, I'm making new pairs. So to break that pair, to break those previous paired electrons, we need to give some pairing energy. So that actually decreases the stability. So now here we have 3 pairs. So crudely we can say 3p. So these electrons are exchanging the upspin electrons. That's why we are getting stability in terms of exchange energy, E3. These electrons, downspin electrons, are also exchanging in between them. That's why we are getting another stabilizing energy term, another E3. And we are breaking these pairs. So that's why we have to apply some energy. We have to expend some energy. So that's why this 3 pairing energy we have to subtract. So now this one is the stabilizing energy that is working for this full field configuration. In the half field configuration, it was only E3. There were no pairing. We were not breaking any pair, right? But in case of full field, we have paired electrons, and to exchange the electrons into the same spin electrons, so we have to give some pairing energy to break those pairs. So actually this E3 plus E3, that is much greater than this pairing energy. So that's why even if we subtract this pairing energy, this value is still higher than this E3 value. So this E3 plus E3 minus 3p, this value is much higher than this E3 value. So that's why this full field configuration is much more stable compared to the half field configuration. Okay, got it? Now let's see the trend of ionization energy along period. So this one is for S and P block elements. So if we go along period, we see that principal quantum number is, this one is along group. So we are going along group. We have already discussed about along period, sorry. So if we go along group for S and P block element, we see the principal quantum number is increasing. That means the number of shell or number of orbit is increasing, right? From beryllium to magnesium to calcium, the number of orbit is increasing. So the size of the atom also increases. So I will try to draw again. If this is the attractive girl, and these are the orbitals where these lower electrons are roaming. So the principal quantum number is increasing as we go from top to down of the group. The size of the atom also increasing because we are putting more and more orbits. Now Z star, effective nuclear charge, is also increasing, which works in the opposite direction. Now we can neglect this contribution. Just to let you know, I am giving this information, but these red ones, whatever I have written in red, so those factors are minor factors. So the increase of Z star or effective nuclear charge is minor in this case, and the increase of radius is predominant. So as the radius is increasing, as these electrons are going far away from this nucleus, so it will be easier to remove those electrons. For example, if we need some energy to remove this electron, if we have another orbit, it will be much easier to remove these electrons because this electron is further from the nucleus and this electron is closer to the nucleus, right? So this electron has lesser attraction to the nucleus. That's why it will be easy to remove this electron. So hence, as we go from top to down of a group, the ionization energy decreases. So that was the case in case of S and P block elements. Now let's see in case of D block elements. So in case of D block elements, when we go along the group from top to bottom, the high effective nuclear charge due to D and F contraction. So the effective nuclear charge increases because of the D and F contraction. So the D and F electrons, they are actually diffused in nature. They have less sealing power. So that's why the further s and p electrons, those are having more attraction towards the nucleus. So the effective nuclear charge is much more to those electrons, furthermost electrons also. And also the penetrating power is, the s orbital is having the more penetrating power compared to p, compared to d, and compared to f, right? So s orbital is having the highest penetrating power. So ns orbital penetrates n-1d and n-2f orbital. Hence, to remove electron from ns orbital, much more energy is needed. Now let's try to understand what is this penetrating means. So I will just give you a crude idea. Now let's see. So we have different orbitals. Just think we have some more energy levels here. Now when we consider this electron, let's put one more orbital here, and let's consider that these are the d electrons we have here. Okay, if we have d electrons here, so these d electrons are actually diffused and they have lesser shielding power. So this attractive girl nucleus will attract this electron or this lover, right? So this lover will try to come close, and actually it will go close, and it will go beyond this n-1d or n-2f. It will go closer than these d electrons and f electrons. So that's why this contraction is also known as penetrating power. This s orbital can actually penetrate this d orbital and f orbitals, whatever present there, and it can go inside. Again, try to understand, when we have more number of d and f electrons, their shielding power is less, and that's why this nuclear's attraction is more in this ns electrons. So these ns electrons will feel more attraction towards this girl, and that will go inside, penetrating the d and f electrons. Clear? So as the effective nuclear charge increasing, as well as the penetrating power of s is much more, hence the ionization energy increases. So we have seen for s and p block elements along group, the ionization energy is decreasing, but in case of d block elements along the group, if we go from top to bottom, the ionization energy is increasing. So this is not exception, this is actually rule for these d block elements. If you go from top to bottom, the ionization energy will increase. Now let's see some comparison to make it clear. Okay, now if we take this group 1 elements, lithium, sodium, potassium, rubidium, and cesium, and we see the first ionization energy, so we can see it is decreasing. As we go top to down, it is decreasing, or we can say from down to top, it is increasing this way, right? In case of lithium, it was having 520 kilojoule per mole, whereas in case of cesium, it is coming down to 375 kilojoule per mole. Same thing we can see in this group 14, carbon, silicon, germanium, tin, and lead. Again, we can see the ionization energy is actually decreasing from top to bottom, or we can say from bottom to top, it is increasing. In case of carbon, the ionization energy was 1086 kilojoule per mole, whereas in case of lead, it is only 715 kilojoule per mole. But now let's see the d block elements. So in case of d block elements, if we see group 4, titanium, zirconium, and hafnium, we see as we go down the group, the ionization energy is actually increasing. In case of titanium, it was 658 kilojoule per mole, whereas in case of hafnium, it is 760 kilojoule per mole. Again, see group 5, vanadium, niobium, and tantalum. So you see, in case of vanadium, the ionization energy was 650 kilojoule per mole, whereas in case of tantalum, the ionization energy is 761 kilojoule per mole. So in case of s and p block elements, as we go down the group, the ionization energy decreases. In case of s and p block elements, whereas in case of d block elements, as we go down the group, the ionization energy increases. So I hope this is clear. So this is not an exceptional case. This is actually rule for the d block elements. Okay. Now these are some conversion factors that you need to remember to calculate any, to do any example or sum. For that purpose, I have noted down these conversion factors. So 1 eV per atom is equal to 96.5 kilojoule per mole, and 1 eV per atom is equal to 23.06 kilocalorie per mole. Now, how to convert this? You can convert this EV. This EV is actually charge into voltage, right? And the charge of electron we know 1.6 into 10 to the minus 19 coulomb, and if you consider that 1 volt, so we get joule per atom. So coulomb multiplied by volt is joule per atom. So we get 1.6 into 10 to the minus 19 joule per atom. Now this is per atom. So if you want to convert it per mole, you have to multiply it by Avogadro number. So if you multiply it by 6.022 into 10 to the 23, you will get the value of EV in joule per mole. Now from this joule per mole, you can convert to it in the kilojoule per mole, and you will get this value. 1 eV per atom equals to 96.5 kilojoule per mole. Now this is the chart which I thought to show you. This chart shows first, second, third, fourth, and fifth and sixth ionization energy of these elements or atoms. For case of in the case of hydrogen and helium, you can see hydrogen has only first ionization energy. That is obvious because it has only one electron, right? So it cannot give more electrons, right? In case of helium, it has first ionization energy and second ionization energy. That is also obvious because helium has only two electrons. So at max we can take out two electrons. Similarly, lithium has three ionization energies, I1, I2, I3. Beryllium has four, boron has five, and rest of the elements can have more ionization energies. We can take out more and more electrons, but yeah, at the cost of higher and higher energy. If you see in case of carbon, first ionization energy is 1086 kilojoule per mole, whereas second one 2350, third one is 4620, fourth one is 6220, and if you see the fifth and sixth, that is way high. You can see this one is 38,000 and this one is around 47,000 kilojoule per mole. Because as you remove more and more electrons, the element will become positively charged ion, and those ions will have much more Z effective or effective nuclear charge. They will have much more attraction towards the nucleus. So it will be much more difficult to remove more and more electrons from the ions. So you can note down these values if you need. And this periodic table shows the first ionization energy of these elements in eV per atom unit. Now we will briefly discuss about the ionization energy of molecules. So earlier till now we have seen the ionization energy of atoms. Now we are going to consider the ionization energy of molecules. So with the increase of electronegativity of the central atom, the ionization energy of molecules increases. For example, if we see the trend in the binary hydrides, so we can see here we have nitrogen as a central atom, then oxygen, and then fluorine. So as the central atom is becoming more and more electronegative, what is the electronegativity that I will show in the later part of this slide or of this lecture. I'll describe this electron affinity and electron negativity, all these things. Just for the time being, just remember, as we are increasing the electronegativity of this atom, the ionization energy increases because the central atom holds the electrons, bonded electrons, more tightly. Similarly, in the case of pH3, phosphorus is the central atom, here sulfur is the central atom, here chlorine you can consider as the central atom. And as we increase the electronegativity, the ionization energy of the molecule increases. Same trend you can see in case of these halo acids, fluorine, chlorine, bromine, and iodine. As fluorine is having, fluorine is the most electronegative element, so it is having higher ionization energy. The HF is having higher ionization energy. So it means in case of HF, if you see this is the HF, and in case of HI, if you see HI, so if you want to take out these bonded electrons from HF or HI, the ionization energy will be much higher in case of HF. So it will be much more difficult to remove the electron from this HF molecule. Now similarly, you can see these other examples. NF3 will be having higher ionization energy compared to NH3, and PF3 will be having higher ionization energy compared to PH3. Yeah, this one I have to explain. See, NF3 is having higher ionization energy compared to NH3, but PF3 is also having higher compared to PH3, but the amount is not very significantly high as expected. Okay, so the ionization energy of NF3 is higher than NH3 by 268 kilojoule per mole, but the ionization of PF3 is higher than PH3 by only 121 kilojoule per mole. So this can be rationalized by considering the 2p to 3d back bonding, p pi d pi back bonding. Now in case of NF3, so this there is no vacant orbital in case of nitrogen, so that's why these fluorines are just pulling the electrons, right? Fluorines are pulling the electrons towards itself. Now in case of PF3, so phosphorus is having vacant 3d orbital, so that's why these electrons of the fluorine, it can actually go to the vacant 3d orbital of the phosphorus, and that can make a double bond. You can see here's a double bond. F plus means fluorine has given its electron to the phosphorus, and all these fluorines time to time can give their electrons to the phosphorus. So this is called p pi d pi back bonding. So fluorine is giving back electrons to the phosphorus. Now because of this reason, you can see there is a potential negative charge in case of phosphorus. So as it is a negatively charged, you can relatively easily take the electron out. Okay. In case of NF3, fluorines were actually holding these electrons, they were dragging these electrons. So as when you are trying to remove electrons from ns3, you have to put higher ionization energy, you have to give more energy. But now in case of pf3, fluorines, yeah, they are pulling the electrons because of the inductive effect, but at the same time, because of the resonance effect or p pi d pi back bonding, they are also giving back the electrons. Now this phosphorus or the central atom is having partially negative charge. This is called a delta negative charge. Delta sign is like this. So because of this partially negative charge, relatively easier it is to remove that electrons, to remove the electrons from pf3. Okay, but yeah, still the ionization energy of pf3 is higher than ph3, because in case of pf3 these fluorines are having inductive effect, they will hold the electrons tightly compared to ph3, right? So there will be lesser, if you see this, I'll do here pf3, and here I will make ph3. So just try to understand ionization energy of these molecules. Although hydrogen is more electronegative compared to phosphorus, but still you can think there is significant amount of electron density on this phosphorus. Now when you have fluorine, that fluorine actually drags this electron cloud towards itself more compared to the hydrogen, right? That fluorines are dragging the electrons. Now the electron density over this phosphorus will be less. It will be there, but it will be less. But it cannot completely reduce this electron density, right? Because fluorine is doing p pi d pi back bonding also. That's why it is also giving it back. Some electron density will come back. So comparatively, we have lesser electron density on this phosphorus. So as the electron density is lesser, so this phosphorus will hold these electrons tightly, right? That's why you have to give some ionization energy to take out those electrons. Now that ionization energy will be higher compared to this pH3. Okay. As it is having lesser electron density, it will hold the electrons much more tightly. And because that, if you want to remove electron from pF3 molecules, that ionization energy will be higher, 121 kilojoule per mole higher compared to the ionization energy of this pH3, right? So no doubt that pF3 will have higher ionization energy compared to pH3. This one is clear. Let's try to understand it again. This one is pH3. Hydrogens are pulling the electron a little bit, but still there is significant amount of electron density in the phosphorus. Now when we have pF3, fluorines are pulling those electron cloud towards itself. Now phosphorus is having less electron density. Now when it has lesser electron density, then this phosphorus will have much more attraction towards its electron cloud, right? So it will tightly hold those electrons. That's why you have to put more energy to take out electron from this pF3. But in the other case, these fluorines, they are actually giving the electron back by p pi d pi back bonding. 2p from 2p of fluorine to 3d of phosphorus. So now because of this p pi d pi back bonding, some electron density is going from fluorine to phosphorus, and that is actually a little bit increasing the phosphorus's electron density. So that's why the ionization energy, which could be much more, that is not very bigger number compared to the pH3. Okay. For example, if I give some arbitrary numbers, just take, for example, this pH3's ionization energy is 100 unit. Okay, 100 unit. Now in case of pF3, if we consider that this pF3, these fluorines do not involve in the back bonding. Okay, if the fluorines do not involve in the back bonding, that time the ionization energy should be around 500. Just arbitrary numbers. Okay. Now as the fluorines are giving back the electron density, so the phosphorus is gaining some electron density. So it is somewhat easier to take out the electrons. So now the ionization energy comes down around 300 or 250, you can say. So actually, if there was no p pi d pi back bonding, the ionization energy would have been much bigger value. Okay, but as there is p pi d pi back bonding, the ionization energy is relatively small, but still it is large enough and larger than the ionization energy of pH3. Fine, is it clear? If you still have any confusion, please go back 5 to 10 minutes and then see the video again. And still, if you are not able to understand, you can comment down below. I will make a separate video on this. So what are the key factors or keynotes regarding this ionization energy? So we have observed that ionization energy is upright property. I will take the laser pointer. So ionization energy is upright property. And do not get confused with the term ionization potential. Okay. So ionization potential is an intensive property measured by volt, whereas ionization energy is an extensive property measured by EV per atom or kilojoule per mole. So ionization energy is slightly different than the ionization potential. Inert gases having highest ionization energy along period occupy the peak positions in the graph, and alkali metals are having lowest ionization energy along a period. From left to right along a period, ionization energy increases for S and P block elements, whereas for D and F block elements, the variation is very less. There is very slight increase. And if you see from top to bottom along a period, ionization energy decreases for S and P block elements, whereas from top to bottom along a period in D and F block elements, ionization energy increases. So this is due to the less shielding effect of D and F electrons, known as D or F contraction or scandite and lanthanide contraction, and higher penetrating power of s orbitals, which I have already explained these things. So this increase in ionization energy along period is not an exception, rather a rule for T block elements. Okay, so these many things you have to remember for the periodic trend in ionization energy.
Hey genius, I hope you liked the video and the concepts are clear. So if you want to know more and if you want to learn more, you can go and check the periodic table and periodic trends folder. I have already uploaded 7 lectures on this topic. Please go and watch all those 7 lectures. I hope it will be very useful for you. And if you think these videos are knowledgeable, please share it with your friends and don't forget to subscribe. Okay? Thank you. Bye bye.